Ideal gas. Recall that thermodynamics studies a physical system with a macroscopic view. A microscopic view of a body of matter considers microscopic properties such as the mass, position, and velocity of each particle, whereas a macroscopic view considers macroscopic properties such as the total mass m of the system, the number of moles lowercase n, the total number of particles uppercase n, the volume v, the pressure p, the temperature T, and the internal energy capital U. These are called state variables because the body of matter is in a state that has a definite set of values of these properties, and all the properties can change, so they are variables. The set of state variables specifies the state of the system, and different states will have different values of at least one state variable. However, not all state variables need to be known to specify a state. For a gas, a subset of 3 is sufficient. For example, n, number of particles, p, and v. The other variables can be calculated from the subset. These 3 variables are independent of each other. We will be studying a gas with a fixed quantity of matter, hence with fixed capital N, and therefore fixed mass m equals nmp, where we assume that all particles have the same mass mp, or m equals nm, where n is the number of moles and capital M is the mass per mole or molar mass. Recall that 1 mole of matter contains a number of particles equal to Avogadro's number, n subscript A is equal to 6.022140.176 times 10 to the 23, approximately the number of atoms in 12 grams of carbon-12, which have 6 protons and 6 neutrons. We will use the value Na equals 6.022 times 10 to the power 23, which is a good approximation to 4 significant figures. If capital N is fixed, then only 2 independent variables are needed to specify a state, for example, P and V. A state can be specified by a different pair of variables, but for now we will stick with pressure and volume, P and V. The important variable, temperature T, can be related to P and V with an equation of state, which is f of P, V, and T equals 0, where f is a function of P, V, and T. This function can have different forms for different gases and has a specific form for an ideal or perfect gas. An ideal gas is an idealized model of a gas, which means that no real gas behaves exactly like an ideal gas, although most gases are approximately like an ideal gas if the pressure is not too high. An ideal gas model has particles that are points with no volume and do not interact with each other except by collisions. A real gas has particles with small but finite volumes, so if it is compressed enough, all the particles will end up next to each other, as in a liquid, and the gas will have a minimum finite volume that cannot be reduced. But an ideal gas can be compressed to 0 volume because its particles have 0 volume. Furthermore, a real gas has attraction between particles, so their interactions modify the internal energy and pressure, whereas an ideal gas has internal energy and pressure that depend only on the motion of the particles, which is simpler to model. An ideal gas obeys the ideal gas law, or ideal gas equation, which is PV equals nRT, where the gas constant R is equal to 8.314 joules per mole per Kelvin. Note that it is essential that the temperature T is in Kelvin, not centigrade. This is very important. At T equals 0 in Kelvin, which is called absolute zero, if the volume is constant, then the pressure is 0, or if the pressure is constant, then the volume is 0. Note that the ideal gas law is an equation of state expressed in another way, since it may be written as PV minus nRT equals 0, which has the form f of PVT equals 0. Since T is now dependent on P and V, we have a way to define the temperature of an ideal gas without using a thermometer based on a thermometric property, which is T equals PV divided by NR. The ideal gas law may be written in yet another way, by noting that the mass of the gas m equals N times Np, the mass of a particle, molar mass m is equal to Na times Mp, and number of moles N is equal to the mass m divided by the molar mass, capital M. So Nr is equal to little m over big M times R, which is equal to capital NMP divided by Avogadro's number times Np times R, which is equal to capital N times R divided by Avogadro's number, which we then set as equal to capital N times Kb, where now Boltzmann's constant Kb is equal to R divided by Avogadro's number and is equal to 1.381 times 10 to the minus 23 joules per particle per Kelvin. Hence, PV equals capital N kBT is another form of the ideal gas law. If number of moles N, or the mass m, or number of particles capital N is fixed, the ideal gas law implies that PV divided by T is equal to NR, which is equal to a constant. Hence, if a gas changes its state by a process from state 1 to a different state 2, with variables P1, V1, T1, and P2, V2, T2, we have that P1, V1 divided by T1 is equal to P2, V2 divided by T2. It will be very useful to represent states of a fixed quantity of gas on a PV diagram, which is a graph of P versus V of the gas. We will assume that the gas is in a container with volume V that can change, and that the gas has a uniform pressure and a uniform temperature throughout its volume. Both P and T can change, but they remain uniform or very close to uniform at all times, so only one value is needed per variable. A state of the gas is represented by a point on the PV diagram. If it changes its state in a smooth process, it will move through a succession of states so that it traces a line or a curve on the PV diagram. A line is made of a series of adjacent points, so the gas moves through all the states on the line as it changes from an initial state I to a final state F. For example, if temperature T is constant in an isothermal process, then from the ideal gas law we have P equals nRT divided by V, which is the equation for an hyperbola. This curve is called an isotherm. Iso means equal in ancient Greek, and isotherm means equal temperature. An isothermal process is one of several important processes that we will study in an ideal gas. We now look at 3 examples that apply the ideal gas law. In example 18.1, we are asked to find the volume of 1 mole of an ideal gas at STP, that is standard temperature and pressure, where the temperature is 0 degrees centigrade and the pressure is 1 atmosphere. We use the ideal gas law, PV equals nRT, and we solve for V equals nRT divided by P. Now remember, the temperature must be in Kelvin, so the 0 degrees centigrade is converted to 273.15 Kelvin, and 1 atmosphere is 101.3 kilopascals, so 1.013 times 10 to the 5 pascals. The answer is 0.0224 meters cubed. There are 1,000 liters in a cubic meter, so we multiply by 1,000 to get 22.4 liters. In example 18.2, an ideal gas is compressed. The initial state has P1 equals 1 atmosphere, V1 not as a value but as a factor times V2, V1 equals 9 V2, so the gas is compressed to 1/9 of its size, and T1 equals 27 degrees centigrade, which we must convert to Kelvin, 300 Kelvin. In the final state, we have P2 equals 21.7 atmospheres, we have V2, which we don't need to know, and we are asked to find T2. So we use the formula P1 V1 over T1 equals P2 V2 over T2 and solve for T2 to get 723 Kelvin, which is 450 degrees centigrade. Note that because V2 is divided by 9V2, we don't need to know the values of the volume. Example 18.3 departs from the usual situation of a fixed amount of gas. We are going to fill up a scuba diving tank. The empty tank contains 11 liters of air at 21 degrees centigrade and 1 atmosphere. You then add an extra mass m of air, and the final state has T2 equals 42 degrees centigrade and P2 equals 2.10 times 10 to the 7 pascals. Find m. The molar mass of air is 28.8 grams per mole. In the initial state, T1 is 21 degrees centigrade, which must be converted to Kelvin, 294 Kelvin. From the gas law PV equals nRT, we can solve for n to find N1 equals P1V1 over RT1. That's the initial state. So the amount of gas that was originally in the tank is 0.46 moles. In the final state, we use the same formula, and we find that in order to have the conditions that we need N2 equals 88.6 moles. So the mass we need to add is the difference, which is the molar mass times the difference in the number of moles, because you're adding additional moles, and that turns out to be 2.54 kilograms of air.